Okay, hello. So this week we have started solving some physical problems involving the vibrations of, systems that, some kind of vibrational problems. So these problems appear naturally in the case of molecules, their vibrational spectra and things like that. So, this is also important in terms of, in some research problems as well. So, but first we are going to start with these kind of toy models. So in here, I'm going to start solving this simplest example, all right? After that, I'm going to go to a more complicated three-particle example. Then in the next week, or perhaps in a separate video, I'm going to talk about the vibrational spectra of the water molecule. Okay, so some of the ideas are going to be developed one by one. So what we are doing in here is we would like to use the symmetry and the group theory to simplify these problems, right? So it's not really classical mechanics. I don't want to really explain the details of these kind of systems, but we would like to show how group theory enables us to solve these problems in a simpler way. Okay. So in any case, so in this problem, we have like two objects with equal masses. They are connected with each other and with the walls with springs like that. So this spring is identical with that spring. And so therefore, because of that, this system has this left-right reflection symmetry, right? So there's some kind of a midline in here. There's some kind of a reflection symmetry. Reflection across this midplane in here. In any case, so because of that, the symmetric group is symmetric group. All right. Symmetric group in that case, well, every group contains an identity. Here we have also the reflection in here. So apart from that reflection, there is no symmetry at all. I should also say that I'm actually interested in this one-dimensional motion here, so I'm going to consider only this oscillation here, and I'm not going to consider this modes in this vertical direction. All right, it's just a one-dimensional problem. Okay. In any case, so this is a very simple group because it's like a cyclic group of order 2. Its representations are also very simple. I'll also talk about that at some point. But we would like to actually see how do we actually pose this problem. Okay. So in any case, what I'm going to do is, first of all, I'm going to try to describe physically what happens. So let me start with this, right? I'm going to copy this picture, and then on the copied picture, I'm going to say something else, right? So let's say it like that. So first of all, this actually shows an equilibrium configuration, right? This is the equilibrium, meaning that position. Once you leave the objects at that position, they are not going to move at all. So as a result, we have an equilibrium position in here for the first object and equilibrium position in here for the second object. So this picture is symmetric. Okay? But when I think about the vibrational motion, these objects are going to be displaced. So let me, I don't know, in that case, I don't want to copy this. I would like to draw a new picture in here. So this is the equilibrium position again, and these are the equilibrium positions. Perhaps the first object is displaced like that, and I'm going to call x1 as the displacement, and the second object is displaced like that. So this is the displacement of the second object, right? So x1 and x2 are displacements from the equilibrium positions. This is usually what we choose because sometimes we make this small displacement approximation. So in any case, the equilibrium corresponds to a position where x1 and x2 coordinates are both equal to 0. And we are essentially looking for the small displacements from the equilibrium position. So here, since the springs are linear, we don't need to do this kind of a small displacement approximation. Yeah, but whatever, I mean, So that's in that case, I mean, this problem is a little bit simpler in a way. We don't have to make any approximation in here. So the springs will be, I mean, some of them are going to get compressed and some of them are going to get squeezed. In any case, basically, we need to use these coordinates. So instead of these, I would like to use a vector coordinate, right? Where x is a vector in a two-dimensional space where the x1 and x2, these two components, are the positions of these two objects. So is a vector, right, in a 2D vector space. So we don't have any complex numbers in here, so we can think of this as a real vector space. Okay. In any case, what does the symmetry mean? So, for example, if you think about the symmetry operation, it was just a reflection across this midplane. That symmetry operation is actually a transformation of this vector in here. So the symmetry operation is a transformation of the vector x. Okay, so x is basically transformed under this reflection, for example, to a different vector. So since this is actually a linear transformation, I can express the second vector as a matrix, 2 by 2 matrix multiplied with x. Okay, so in any case, this is going to be our representation actually. So let's say it like this. A is actually a representation from the group to the 2 by 2 matrices. Okay, so so basically A is a representation. A is a representation. In a way, that representation is actually determined by the setup of the problem and not with the physics, right? I mean, it doesn't depend on, for example, spring constants in here, for example. So as a result, I mean, in a way, that representation tells us how these coordinates transform under this symmetry transformation. Okay, so what we are going to do is we are going to find the decomposition of that representation in terms of the irreducible representations of the group, and we are going to see why this is useful for us. Okay, but at some point I need to start describing the physical problem as well. Okay, but I mean, let's just do this. So to be able to do this, I first need to now find what that A sigma is. So there are actually two matrices. Well, identity, for example, this is just an identity matrix. I also need to find A sigma, right? So that's a 2 by 2 matrix. And in that case, I just need to look at this transformation in here. Okay. So, for example, if I'm just going to do it in that corner in here. Okay. So that's my picture. Okay. So let's say that these are the equilibrium positions. The equilibrium positions are situated in a similar way. So let's say that yellow is the displacement pattern of these two particles. So I'm just going to exaggerate this one. So in any case, after a reflection, so I'm going to use a blue color, for example. In that case, this particle in here is going to move to that location. I exaggerated actually a bit more, but yeah, it's going to be somewhere in here. And this particle is in here, right? So let me do it again. So this is the first particle, that's the second particle. So the first particle will move in here and the second particle is going to move in here. In any case, in here, I'm basically going to get a new position for the first particle, which is equal to the negative of the original particle of the second particle, right? So the x1 prime therefore is equal to minus x2, and in the transformed configuration, the second particle's position is equal to the negative of x1. Okay, so therefore the transformation is from x1, x2 into minus x2 minus x1. Right? That's the transformation. So This is the transformation from a position vector to a new position vector, which is obtained from the old position vectors like that. But I would like to express this as a matrix expression. So in that case, in terms of matrices, it's just the multiplication of that matrix with the original vector gives us x prime. Okay. So therefore, that matrix is the matrix representation of the reflection operation. So the identity is represented by the identity matrix. Reflection is represented by this matrix. Okay. So A is a representation, meaning that well, if I have like two operations, their product, the product of the matrices is equal to the representation of the product of the operations, or something like that, right? So in this case, it basically tells you that the A sigma squared is equal to identity. So yeah, whatever. So therefore, I mean, this matrix is the inverse of itself, right? Because the sigma is the inverse of itself, you know. Okay. So in any case, I mean, let's just go ahead with the decomposition actually. So this is a matrix. It's not an in block diagonal form. So we would like to put this into this block diagonal form. So as a result, we need to talk about the representations of the group G. So first of all, let's construct a character table. So this group is an abelian group, which means that every element is a conjugacy class by itself. So we have the element identity, conjugacy class, and the element sigma, right? So each one has one element, so that part is simple. So there are two representations, therefore. The first one is a trivial representation. All of these representations are one-dimensional, so therefore the first column is all ones. What we are left is that element in here. So in that case, I use the fact that sigma squared is equal to identity. So therefore, A sigma squared is, sorry, for any representation, therefore, U2, for example, U2 sigma squared, therefore, has to be equal to identity matrix. But this is just a number, so that means, just a moment. Just a matrix, one by one matrix. And so therefore it's just a number. So that number can only be equal to plus or minus one, therefore. Okay? So that can be either plus one, but in that case, I get the same thing as the first row. I mean, the second representation must be different. So therefore, the only possible thing here is for this number to be equal to minus one. Okay. What I usually do in here, I mean, that's the character table. I also write down the characters of my representation. So in here, for example, the character of identity is equal to this trace, character of identity, that's equal to 2. And the character of that representation is again the trace, sigma. It's the trace of that matrix that's equal to 0. So these are the characters. Yeah, I'm not going to leave that in here, right? I'm just going to leave that there. I'm not going to raise them. So that's 2 and 0. Now, by using the characters, we can find the decomposition easily, right? That's what we are going to do. There's some kind of a formula for finding how many times, for example, U1 appears in the decomposition of A and things like that. If the representation is really huge, you can do that. But here it is quite easy to see that the first row and the second row summed up gives me the third row. So that tells me that therefore the A is a direct sum of U1 and U2. Okay. It is decomposed as a direct sum of these two representations. Well, what does it mean? Well, it means that it means that A has an invariant subspace. Let me say it like that. So of vectors that transform like U1. Okay. And it also has an invariant subspace of vectors that also transform like U2, right? That decomposition is actually a decomposition of the subspaces. So we can clearly identify this, actually. So what I'm going to do in here is, again, I'm going to use this pictorial device. Sometimes these can be useful, sometimes they are not. Here they are useful. So first of all, let's think about some kind of a particular displacement of these objects. Like, for example, this is displaced by a small amount, and that's displaced by a large amount, for example. X2 is bigger than X1. So that basically corresponds to a point somewhere in here. So X is a point in here. So here, I'm not considering X as a matrix, but I'm considering as a vector in a two-dimensional space, or a point in that space. Okay? So under a reflection, that point is transformed to this point. Okay, so I'm going to use a yellow color for this one. So a reflection is essentially a transformation that maps this point, that sends this point to that point. So this A sigma, the reflection, essentially moves that point to that point. Okay, I'm going to use this picture to identify the subspaces, which are kind of obvious actually. There's this subspace, well, this diagonal in here. Okay, I'm going to call this as line, sorry, line 1. Okay, so that's line 1. Basically, these are vectors that transform like transforms like the U1 representation. What was the property of the U1 representation? Oh, in the U1 representation, vectors remained invariant. So therefore, I mean, all points on that line actually are vectors that remain invariant. So this A sigma essentially can be thought as some kind of a reflection across this mirror, right? This pink line is our mirror. We are doing a reflection, so therefore every point on the mirror remains there, right? It's mirror images itself. So this is basically line which is parallel to, I can think of it like that, the set of vectors where the x1 component is equal to minus x2, or you can think of the line 1 as like the line 1 is the linear span of the vector 1 minus 1. Okay. There's another line in here. I'm going to use the blue color for that, or a red color. So probably red is better. So it is that diagonal. Okay, so it turns out that these two invariant subspaces are perpendicular to each other. There's a 90 degree between them. In any case, so that's line 2. So that's line 2. Basically vectors that transform like the U2 representation. So these are basically the set of points where x1 is equal to x2. In that case, any point in here on that line is going to be transformed to the exact opposite, okay? So let's say it like this. I mean, let's just remember again the U1 and U2 representations. Sorry, there's identity and sigma. Under identity, the transformation appears like multiplication with 1. Under reflection, the U1 appears like multiplication with 1, and U2 appears like multiplication with U2. So therefore, let's say it like that, all right? On line 1, for example, under a reflection, the vector does not change. So therefore, it basically transforms like this. On line 2, the vector under reflection is going to change to minus x, right? It's going to change sign, so therefore, in that case, replace reflection is equivalent to this. Okay, In any case, I mean, by using this, you can easily compute what the, how this point actually transforms. Sorry, I think I didn't draw this correctly, but I mean, this distance should be exactly the same as that distance, and this distance and that distance are exactly the same. Okay? So in a way, this red line is the reflection line. So on that line, we are reflecting, the vectors change sign. The pink line is the mirror line. So we are doing a reflection across this. In any case, what's the use of these two invariant subspaces? We can actually make a change of coordinates. Right? Change of coordinates. Right? From x1, x2, we would like to change to a different coordinate. So I'm going to call these like y1 and y2. So these are the normal mode coordinates. Normal mode coordinates. What are normal modes? Basically, the normal modes are, for a problem, are solutions of the equations of motion that have a definite frequency. Okay? So we can actually, passing to a normal mode actually implies that each one of these coordinates actually satisfy an equation of motion where there is actually only one frequency that appearing there. So, I mean, that's actually what we imply. But at this point, it's actually quite hard to see that these are really the normal modes. But the symmetry kind of tells us that if I choose my coordinates like that, I mean, if I choose this as my y1 axis and this as the y2 axis, then these are like the coordinates. So I'm going to show you how we can do this. Okay. First of all, I'm going to start with these x1 and x2 axes. Sorry, x2. And then I'm going to draw this y1 axis. Y1 axis and a y2 axis, right? So I'm going to use the same colors again. So it's y2. So all of these angles are 45 degrees, right? Let's just remember these. So these are 45 degrees. In any case, how do you do this transformation? Basically, it's a transformation from my x vector to a y vector, right? And how we can express this transformation is what I'm going to explain now. So what happens in here is this something like that. So suppose that I have a vector in here, an arbitrary vector. Okay. So that's the vector x, for example. But let's just think of it as some kind of a vector in here. I mean, that's the vector x. Sorry, I'm going to use this argument in here. So x is equal to, basically, we write the matrix like that. So that's the x1 coordinate and x2 coordinate. I can think of this as like x1 multiplied with this unit vector and x2 multiplied with the other unit vector. Okay. So in any case, I mean, in physics, this is basically what we do, right? There's some kind of a unit vector in here along this direction. So let's just call this as E1. So I'm going to erase this and, well, basically x1 multiplied with E1 summed with x2 multiplied with E2 gives us the vector, right? I mean, that's the thing that we are actually using in here. Okay. So what I'm going to do is to express the same vector in terms of, well, basically, I'm going to define some kind of a unit vector along that direction. Right. Sorry, wrong color. A unit vector along that direction. That's also wrong. All right. I'm going to define a unit vector along this direction. So I'm going to call this as E1 prime and a unit vector along that direction. Along this direction. So I'm going to call this like E2 prime. So as a result, the same vector can be written as y1 times E1 prime plus y2 times E2 prime. Okay. I'm going to consider this equation, but except that I'm going to write it in terms of the matrices. So I'm going to write this equation again. So that's the X matrix, which is x1, x2. That can be written as y1 coordinate multiplied with the unit vector along that direction. So that's 1 over root 2, 1 minus 1. Why do I have 1 over root 2 in here? Because it's a unit vector, okay? and then y2 multiplied with that unit vector. So that's going to be 1 over root 2, 1, 1. Okay. I can think of this as some kind of a matrix expression, right? So it's like a 2 by 2 matrix multiplied with a vector with a coordinates y1 and y2. Let's just keep in mind that this y1 is multiplied with the first column in here, which means that I need to place this vector into the first column. I have already written down 1 over root 2 in here, but I just need to write 1 minus 1 in here. Okay. So the first column in here is my first unit vector. And the second column is going to be in here, right? The second column is going to be that unit vector. So you can see that this expression therefore corresponds to that matrix. Okay, so therefore, basically x is equal to some matrix in here. I'm going to call this as x times y. Okay, so I'm basically making a change of coordinates in here. Change of coordinates. So instead of x, I'm using the y coordinate, and the y is given by using that S matrix. Okay. Why do I do this? Because I have a representation, A, basically, which is expressed in terms of this x coordinates. But that representation is going to look simpler if I express it in terms of the y coordinates. Okay. Just notice that I haven't actually said anything about the physical problem right now, right? I mean, the spring constants and masses and things like that, equations of motion, they didn't enter in here. I'm just writing down. I'm basically trying to find the new coordinates where this symmetry transformation appears simpler. So in that case, I have chosen my coordinates to be the coordinates along these invariant subspaces. And I have somehow identified how I can make this transformation from my old coordinates to the new coordinates. So it turns out that these are the normal mode coordinates. Okay, so here the S matrix is this. You just notice that this is orthogonal because the columns are orthonormal vectors. So that means the inverse of this matrix is equal to its transpose. So therefore, it is that matrix, right? We may or may not need this matrix, but I'm just writing in any case. So in any case, so our transformation, right? This symmetry operation. Symmetry operation, for example, under reflection, sorry, x is transformed into x prime, which is given by a sigma times x. I mean, let me consider this in general, right? For any element of the group. So in that case, the group has only two elements. One is either, but let's just say that it's okay. So the question is like, if I use y coordinate, the same transformation, how does it look like? I'm going to call the representation as A tilde, because it's essentially the same representation, but expressed in a different values, right? So that's for all G in the group. How do I do this? Well, I'm just going to use this expression in here. Okay. So I know that x is equal to s times y. So x prime, the transformed coordinates, is equal to s times the transformed coordinates. So I know that x prime is equal to agx. So therefore, that's equal to ag times sy. So that means y prime is equal to s inverse ag s times y. So therefore, that matrix should be the transformation matrix. Okay. So I'm essentially changing the representation A to a new representation A tilde, which is given by S minus AS, right? These two representations are equivalent, so it has the same decomposition, but now I have a different set of matrices. Now the idea in here is this A tilde is block diagonal. Right? So basically, A tilde identity is still identity, obviously, but A tilde sigma is basically is block diagonal. Basically, along the y1 direction, the y1 coordinate does not change, and along the y2 direction, it changes. So basically, sorry about that. So if I have y1, y2 coordinates, under reflection, the y1 coordinate doesn't change, but y2 coordinate changes sign. Okay. So y1 is the axis where the mirror was. So as a result, the transformation in here is this. So the idea in here is that this is both diagonal. So I'm going to use this thing in here. So there are these two diagonal blocks in here. They are one-dimensional. They also correspond to the irreducible representation. So let me erase these, and I'm going to write this in general. Right? In general, I mean, it's not that general actually, but let's say A tilde G is equal to, we have one by one block in here, which transforms like the U1 representation. And there's another one by one block in here, which transforms like the U2 representation. Okay, so that's what we wanted to do. Okay, so sometimes we actually identify that S matrix in here and do this explicitly, do that transformation explicitly. Sometimes we don't, right? We know that such an S exists. We don't identify this transformation, but we just identify this the diagonal blocks in here. Okay, these are identified by simply the decomposition of our representation. Right. Let's come to the basics. Let's come to the come back to the equations of motion. Right. I'm going to claim that these equations of motion are going to be simpler in terms of when they are expressed in terms of this y coordinates. Why? All right, I'm going to perhaps cut the story short. Okay, so I'm going to, I mean, there's actually a Lagrangian formulation actually that we have to follow. I have explained this in the notes, so therefore I don't want to do the explanation in here. I don't really need to, I don't want to use the Lagrangian explanation, but probably I have to, sorry about that. So in any case, Lagrangian is the kinetic energy minus the potential energy, if you remember. So the kinetic energy can be written as, I mean, in this case, it's basically 1/2 of m times x1 dot squared plus x2 dot squared, right? And the potential energy is, well, this part is complicated, but I can actually express it like that. It's actually a quadratic function of the positions. There's some kind of a complication in here, in any case. So there are some coefficients in here, but I and j basically runs from 1 to 2. So I can think of this coefficients as a 2 by 2 matrix elements of a 2 by 2 matrix. I can also consider the first term like that. So this is in general like that, right? This is again a sum over I and j, xi dot mij xj dot. Where m in here is a 2 by 2 matrix again. This time this is diagonal, but I mean, yeah, usually it is diagonal, and the diagonal entries are equal in here accidentally, but I mean, there might be some systems where there might be objects with different masses. So therefore, this is not a rule, but I'm just going to solve the problem for this case where all the masses are the same, right? In any case, let's see. So I can think of this Lagrangian as a matrix product like that. So the kinetic energy involves the velocities, and the potential energy involves the spring constants. Okay, so the equations of motion are the Euler-Lagrange equations. So for every coordinate, we just compute this expression and then set to be equal to 0. In any case, in this case, this basically corresponds to this equation, right? Mij sum over j xj dot, sorry, there is a dot in here, second time derivative. is equal to minus Kij xj. Right? There's a summation. I don't want to actually deal with this kind of an equation. It's actually m times x dot dot is equal to minus kx. Right? Our equation can be expressed as a equation of motion can be expressed as a matrix equation, but there are actually two equations in here. But I can express them in terms of a linear equation. So that's our equation of motion. Okay. So the symmetry, what's the symmetry in here? Symmetry. Okay. Well, if we have a Lagrangian, it actually says that the Lagrangian L is invariant under all of the symmetry operations. Okay, so somehow this is a function that remains invariant. So it tells you that if you consider the Lagrangian as a function of the velocity and the positions, if you compute this velocity and position in terms of the transformed coordinates, so again, it's like x prime is actually obtained by a symmetry transformation, they should have the same value. Okay. All right, so that's basically the symmetry condition. So this implies some kind of a regularity of these equations of motion, but usually we deduce this regularity by the invariance of the Lagrangian. All right. So there are some certain reasons why this must be so, but I don't want to go into these. So in our case, that transformation is, well, first of all, just notice that this is the same transformation of the velocities. So the velocity is also transformed like that. And you just need to look at this expression in here. So the Lagrangian is 1/2 of x dot transform mx dot minus 1/2 of x transpose kx. This should be equal to x prime dot transpose mx prime dot minus 1/2 of x prime transpose kx prime. Okay. Inserting this matrices in here, so therefore we have like x dot ag transpose in here, agx, and similarly in here, x transpose ag transpose kagx. Okay, so I can think of this as some kind of a new mass matrix, and this is a new spring constant matrix in a way. So the mass matrix is transformed into some other matrix where the transformation is like that. But because of symmetry, this must be the same as the same mass matrix, because, I mean, this Lagrangian should be the same as this Lagrangian in here as a function. Okay. So the spring constant matrix 2, it actually normally under this operation, it should change, but because of the symmetry, it doesn't change. So that's our symmetry statement. Okay. In any case, so I mean, let me quickly do this. So this is our equations of motion. So mass times x dot dot is equal to minus k times m. I can express it like this: x dot dot is equal to minus m inverse times k times. Sorry, I made a mistake in here, so it's an x actually. Right, times x, right? In any case, so that's our equation of motion. Okay, so this is the matrix that we would like to compute the eigenvalue. So let me also talk about this. So the normal mode, right? Normal mode is a solution, solution where this x in here, which is a matrix, if you remember, right? It's a column matrix, is equal to some kind of a vector, right? I'm going to call this as a vector in here, a column vector, multiplied with cosine of omega t. Okay, it's actually a mode where the displacement pattern doesn't change, but the displacement actually change periodically with a single frequency. Okay, we don't have many terms in here. Here we just have a single frequency. Right? In any case, so in that case, x dot dot, I mean, this cosine can also be sine as well, or there can be a phase factor, phase angle in here. So that's also a possibility. That doesn't change anything. So in that case, x dot dot is equal to minus omega squared times x. Okay. If I insert this in here, the equation of motion, therefore, is converted into this. So we get minus omega squared times x in here and minus m inverse k times x. X has a time-dependent factor in here, but I would like to express this in terms of this time-independent thing. So therefore, this is m minus 1k, which is a matrix multiplied with v is equal to omega squared times v. Okay. So therefore, we just reduce this to an eigenvalue problem. V is the eigenvector, right? This is usually called the mode pattern. I mean, in that mode, how the different particles oscillate. Omega squared is the eigenvalue, the corresponding eigenvalue. So I can therefore determine the frequencies of oscillation by solving this eigenvalue problem. Okay. So as a result, there is a problem in here. So I'm just going to call this as H, right? Don't confuse this with Hamiltonian. Sorry about that. So probably that can be confused. So let me call this as W, right? That's the matrix that we need to deal with. Okay. So in any case, so therefore we would like to find the eigenvalues and eigenvectors of that matrix. Okay. So we know how the mass and the spring constant matrix transform. How does this W transform? Well, W is equal to M inverse K. So therefore it transforms into, let's see, AG transpose M, AG inverse. I made a mistake in here. Sorry. AG transpose K AG, which is equal to, well, AG inverse M inverse AG transpose inverse of AG transpose K AG. Okay. So in any case, that matrix transforms to that one, which is just this, right? I mean, normally it transforms under any symmetry operation, any operation like that, whether it's a symmetry or not. So if the operation is not a symmetry, then you're going to get a different W matrix in here. However, if G is a symmetry operation, then we know that we already get the same matrices in here, same M and same K. So therefore, we get the same W. Right? So therefore, that's the symmetry condition. Symmetry condition is that this W matrix transforms like that, which is equal to W. Okay. So under the symmetry operation, the W matrix does not change. Or I can use it like this. Well, AGW is equal to WH. Okay, so that's a better symmetric condition. So W commutes with all representation matrices. Okay, and then we use Schur's lemma to simplify this W matrix. That's basically the idea in here. But in any case, so this is actually for the symmetry operation expressed in terms of the old coordinates. In the new coordinates, I mean, just remember that X is transformed into a Y coordinate. So all the representation matrices actually are transformed into new representation matrices. And W, therefore, should be transformed into a new W matrix, right? So the mass matrices also can transform like that. In any case, I mean, you can actually show that this is also is going to transform like that, but I'm not going to show the step in here. So in any case, so that's basically an equation in terms of X, But if I express these things in terms of the new coordinates Y that we have defined, in that case, the commutativity relation is just a commutativity relationship for these transform matrices, right? I mean, if I express this symmetric condition in terms of these normal mode coordinates, we get this. Why did we do this? Okay, so that's the final thing. So in any case, I mean, in terms of these new normal mode coordinates, since these are block diagonal, these W matrices are also block diagonal. That's the idea, actually. And that's the idea that you can use. So because of the fact that AG tilde is equal to, this is in block diagonal form, so there are these two blocks in here. This expression actually implies that the W tilde matrix is also in the block diagonal form, and these two off-diagonal blocks are exactly equal to 0. So there's just one term in here, and there's another term in here. So the W tilde matrix is already diagonal in here, which means these are the eigenvalues. So omega 1 squared therefore is equal to A, and omega 2 squared is equal to B. So these are already eigenvalues. So in a way, what we are saying is that if you use the group theory to define these coordinates, the y coordinates in here, in such a way that your representation is in block diagonal form, in that case, the physical problem that you would like to solve, basically finding the eigenvalues of that matrix, becomes simplified because it's already diagonal. Okay, so as a result, you don't need to solve an eigenvalue equation separately. Right, that's essentially what it says. So I don't have much time in here, but this is also what I have done in class. I have actually identified these two modes. So let's just call this like U1 mode. This is the mode where the mode pattern is like, I don't know, let's say it like this. If first particle is displaced by epsilon, the second particle is displaced by minus epsilon. Can I do a pasting here? Sorry about that. Let's not do that. So let's say that this is our equilibrium position. That's another equilibrium position. So these are the equilibrium positions. So in that displacement pattern, my first particle has a displacement like that, and the second particle has a displacement in the opposite direction. Well, it's basically minus epsilon, right? So it's also displaced by epsilon, but in the opposite direction. So in that's the U1 mode, right? In that mode, this spring is expanded, and that spring is also expanded, but this spring is compressed, for example. And in the opposite motion, of course, the particles are going to go in the backward direction, in which case this and that is going to be compressed, and this will be extended, right? It's just the oscillations in there. So that's a U1 mode. It has a frequency omega 1. There's another mode in here. This is the U2 mode. On line L2, if you remember. So in that case, this thing has a displacement epsilon from the equilibrium position, and this one too. Okay. In that case, something strange happens. So this becomes extended and this is compressed. But the spring that connects these two masses, these two particles together, this K prime, the spring with spring constant K prime, it's not compressed at all. Okay, so there's actually a spring in there. So in any case, so the mode pattern in here is epsilon, epsilon, and so therefore this has a frequency omega 2. There's a nice practical way of actually computing these frequencies. So for example, for this one, since the omega 2 cannot depend on this K prime, I assume that this K prime actually doesn't exist at all. I just remove the spring in there, so the mode is still there, but the spring constant K prime is taken to be equal to 0. Right? So you just assume that there's no spring in there. So in that case, I have like an object with mass m is connected to a spring. An identical object is connected to a spring with an identical spring constant. So they are doing this motion in here, but if you just look at the motion of that mass, for example, you're going to see that it's going to have a spring constant. Sorry, it has a frequency of square root of k over m. Okay. In this case, there's actually a very nice simplifying feature. You just place I don't know, something which is immovable at the midpoint in here. In that case, your problem actually is converted into this problem where I have a mass m connected to a spring, and another spring connects it to this midpoint in here, but this spring is just the half of that spring constant. So it turns out that in that case, the spring constant is equal to 2k prime. In any case, so in this case, it turns out that these two springs can be considered as parallel connected springs. As a result, the net spring constant in that case is equal to k plus 2k prime. And so therefore, the frequency of the oscillation is this. Okay, so let me leave it in here. So perhaps I can say something more about the other problems where the symmetric group is a little bit more complicated. But I'm going to shoot a video about this water molecule problem, because this actually needs a little bit more explanation, because the space is actually much bigger in that. All right, I'll stop here.